This is Computer Programming 1 from the University of Washington. I'm Martin Dickey. Our topic today is nested data structures. And in case you're worried that this course has morphed into an avian biology course, don't be. We're still talking about programming. Nested refers to putting one data structure inside another, and we'll see good reasons why we might want to do this. We'll talk about data representation in C, and then talk about several ways of combining arrays with structs. For example, we'll see arrays of structs, several examples, and also structs which contain arrays. At the end, we'll take an application, namely sorting an array of structs which represent students. In this lecture, we'll be able to apply material from a number of previous lectures in the series, including sorting, and see how that can be combined with the new knowledge we present today. Data representation in C starts with the simple data types that we've been familiar with since the beginning of this course: int, double, and char. Sometimes we call these atomic data types, not because they're going to explode on us, but because they can't be pulled apart into any further smaller components, at least not within the usual context of C programming. We've also seen two ways of representing data that's not composite, that is not atomic, that is composite. We can do this with arrays, and we can do it with structs. Composite data with arrays would represent a series of variables which are all of the same type. And as you remember, and have seen a number of examples of by now, we name the whole collection, the array, and then we number the elements. Structs are collections of fields of possibly different types. Each of these fields has a name that we refer to in order to pull out the field. Now, a key point in proceeding from where we are is recognizing that what we have inside an array or inside a struct could be any type. There's no restriction at all on what type that might be. In particular, and here's the key thing, those things could be arrays themselves, or they could be structs themselves. And in fact, we could continue to nest. The internal arrays could themselves contain structs, which could themselves contain other structs or arrays to as much depth as we wish. Let's take an example of this that involves only structs within structs. Here you see three different struct types defined. One is called point, contains variables x and y. One is called dimension, contains variables height and width. Both of these are geometric concepts that we might want to treat as primitives in a graphics program. Now, at a higher level, we have a concept like a rectangle. It has both a dimension and it has a point, or perhaps multiple points in reality, inside it. So a nice way to abstract this is to make up a new type called rectangle, but take advantage of the definitions we already have for points and dimensions inside. This might be easier to see with a picture. On the left-hand side, I've repeated the declarations and added something at the bottom. Remember that in C, type defs don't allocate storage. They're not variables. They're simply patterns that we can use to define variables later. So at the bottom of the left-hand column, I've put a variable declaration. The variable r is a rectangle, so it will actually occupy storage, and we could draw a picture of what r looks like. This is shown on the right-hand side of the screen. The box, everything inside the box is variable r, and inside are the fields or components which make up r. Let's pick this apart to see how we can get down to the smallest pieces of r. Remember that we use the dot operator to get inside a struct variable. We'll continue this iteratively or repetitively if we have a struct within a struct to get inside the inner struct. R is the whole picture. Now, if I want to get the blue box, that is one component of R. And so if I say R dot lower left, that gives me the entire inner circled region, lower left, which was of type point. Within lower left, there is an area called X. And if I want to pick out just X, then continuing this logical progression, I would say R dot lower left dot X. Note that the dot X has to follow lower left. If I tried to say R dot X, it would make no sense. X is not a direct component of R, it's part of lower left. That example shows a struct within a struct. Let's see one of several ways we might combine structs with arrays. One struct represents a single record or collection. In many computer applications, we deal with collections of these collections. We'll have many student records in a university, many employee records in a company, and many parts records in a factory, and so forth. We'll have multiple instances of one particular record type. I read a very good example of this just yesterday. One very famous long-distance carrier, which I won't name, has to keep track of all the long-distance calls made over its network. And you can imagine what information it needs. It needs to know the number called, the date, the time, and so forth for billing and accounting purposes. This company has to keep track of 250 million of these calls a day. Each one of the calls has information following a single pattern. Together, we might think of them as a large array of structs. Actually, in the programming, a company like this would probably use a higher level data organization technique, a database, rather than an array of structs. In our programs, however, arrays of structs are the natural way to group data of this sort. Let's look at the example on the left-hand side. At the bottom, you see a declaration for something called Pentagon. The variable is named Pentagon. We know it's an array of size 5 by the qualifier that follows the word Pentagon. And we know that the individual components are of type point, the same point that I had on an earlier slide. So the way to picture this is as a set of 5 boxes that are adjacent to one another, showing that they're the elements of an array. Each of those boxes contains the point variables x and y. If I write an expression like Pentagon sub 1, I no longer have an array. Pentagon is the array. Pentagon sub 1 is a single point inside that array. It's a struct. Let's get even deeper into this structure. If I write Pentagon sub 4 dot x, now I don't have an array and I don't have a structure either. What I have is a single double variable. Now, we could apply this in reverse as well. We could have an array inside a struct. A very typical example of this is using a string inside a struct. If I'm keeping information about students, I might want to know a student's name. The way we represent this kind of information in C is with strings, and we know that they are actually arrays of characters. So the student record itself is a new type, it's a struct, and inside variables of that type we'll have an array called name. Since we're going to be using nested structures of different types, we'll find ourselves using them in functions quite a bit too, as parameters and as arguments. So let's take a minute and review what we know about parameter passing for these sorts of things. The rules I'm going to review are not new. They're what we've already seen for passing parameters with arrays and structs. Remember that structs are passed by value. That is, all of its components are copied from the actual parameter. And the formal parameter in the function definition receives a copy rather than a pointer. So in this little bit of code, I have the header or prototype for a function midpoint. The details are not shown. It has two parameters called a and b, which are points. So in main, when I call midpoint, as I've done in this example, what I pass in needs to be a point. So at the time the call is made, the point P1 will be copied to the point A, and the function midpoint will be operating on that copy. Now, if we pass an array of structs, the top level organization is that of an array, and the rule for array is different from structs. Arrays are passed by reference. They are not copied. So look at the example here. The function going to be called is average, AVG. It has one parameter, which is an array. Notice the interesting type of this array. Its elements are all student recs. So when I call it from main, what I pass in should be a variable which is of the same type. Let's see if it is. Average gets AVG with the parameter or argument CSE 142. Checking back to the declaration of CSE 142, we see, aha, it is an array and the type of its elements are student rec. The fact that it's an array and the type of its elements have to match up, or this would not be a legal call. These ways of looking at parameters by matching types is very useful in figuring out what's legal and what's not. This reminds me, when I teach a class, I like to give quizzes, but I don't like to give pop quizzes. So let me alert you right now, there will be a quiz later in this lecture. But since I've announced it, it's not a pop quiz. You'll be prepared for it. And a hint, it has something to do with figuring out the types. Well, don't panic. Just stick with me, and I'll give you all the information you'll need to answer the questions on that quiz. Let's take another application that involves sorting an array of structs. This will give us a chance to review not only arrays and structs, but also sorting, and a little later on, strings as well. Tie together lots of topics we've seen recently in this course. Sorting means putting things in order. Here I have an array of students. Each student has a name, an ID, and a GPA. Now, if I'm going to put these in order, I've got a question to answer first. What do I want to put them in order by? I've really got three possibilities. I could do it by name, by ID, and by GPA. And perhaps in different applications, the answer would be different. Let's look at putting them in order by, well, let's see. What do we have here? Is it by name? Now you can rule that out pretty quickly. Is it by ID? And if you look at the second and third pair, it can't be ID, but it could be GPA. So let's work on a sort that would take this and print a nice list in GPA order so the professor could see who's at the top and bottom of the class. Here's the struct type definition we'll use for student record with the three variables inside it. Now, instead of developing the sort algorithm from scratch, let's be smart programmers. Let's try to do some code reuse. Let me dig up that code that we developed for selection sort and see if we can't adapt it. Here it is. You might remember that there were two functions involved. There was a higher level function, selection sort, which took an array and the size of the array, and that it repetitively called a helper function called minloc, which found the minimum location, following which the selection sort function could swap the value in that position with the value it was currently trying to establish. Here's the code just as we saw it. The reason we can't use it exactly as we developed it is because of the types. We developed this to sort arrays of ints, and now we have something of a different type, an array of student recs. So we'll have to make some changes. We'll also have to make some changes for the min-loc function. Here's the original version of it. And like the selection sort function, it was developed for a particular type, array of integers. Let's think about what changes will be necessary. We'll also have to change the swap function or write a new one. It also depended on the type of its parameters, int stars, and we'll now have a parameter type of student rec star. Well, we've already done the first step. We have to decide which field we're going to sort by. This is usually called the sort key. We've decided to sort by score, the GPA. Now, anytime you see an array type in the program that was int before, we'll have to change that to student record. That should be easy to do. We'll also have to change the comparison. Sorting is essentially a matter of comparing to see which element comes first. We're now going to have to reach inside the student record, pull out the score field, and compare those score fields to make the sort work right. We'll have to write a swap function for student record. And if we apply this analysis to the original functions, we'll see the changes, as I've shown here highlighted in pink. Interestingly enough, the main function has very few changes. In fact, it appears that the only change we'll have to make is the parameter type. Now, you should verify this by going through the code and making sure that all the statements we wrote before are still valid and will still operate in the way we intended them to. In the min-loc function, we have slightly more changes to make. We'll have to change the parameter type again. And then we have this crucial bit of pulling the scores out of the record in order to compare them. So here we have to carefully be sure that we have the right concept, that is, we're pulling the correct value out, and that we use the right notation. B is an array, so the first thing has to be a subscript, B sub something. J tells us where we were in the array, just as it did when B was an array of ints. Once we've got B sub j, that's a student record, so we can apply the dot operator to it and pull out the score. This is the change I'll have to make to the min-loc function. As with the other function, you ought to go through the rest of it carefully and make sure there aren't changes we've overlooked or that something won't work the way we want it to. Finally, you'll have to write a swap function which has a student record star as parameters instead of an int star. We'll leave that as an exercise for you. It's a little bit of practice in using pointers. Okay, we've solved that problem. We can sort now by the score. What if instead we want to sort by alphabetical order? Maybe we're going to call roll, or we have to match our roster against somebody else's roster. In that case, the outcome will be a little different because what we're ordering by is different. Somehow, the algorithm will also have to change. And somewhere in this algorithm, we're going to have to be doing a comparison. But this time, the comparison is not between two doubles or between two ints. It's between two strings. Now, that at first might present a problem. You remember from the string lectures that we cannot directly compare two strings. And the reason was strings are arrays. C does not let us directly compare two arrays. Well, it's not hopeless. We could possibly write our own function, or we remember there's a string library and that it has in it a nice already written function for doing string comparisons. If we review that function, remember how it works, follow the rules it's expecting, we won't have to write that comparison ourselves. Let's just review that briefly. The function is named string compare, strcmp, takes two character arrays as its arguments. It's assumed that those are valid strings in the sense that they have that notorious null character to terminate them, because the string comparison does not know otherwise what the length of those arrays is. The other crucial fact about string compare to remember is it doesn't return true or false. It's not a Boolean. It returns one of three values. negative if string 1 is less than string 2, 0 if they're equal, positive otherwise. So when we write our function, we'll have to refer back to this as a reference to decide exactly how the comparison should be done and what we should do with the result. Let's look at the changes required for min-loc. As before, I have to change the type in the parameter. But now I have a little bit more to do in the comparison. It's not enough simply to pull out the name from each of the records being compared. I can't compare them directly, so I'll have to apply my string comparison function. It returns a negative, a 0, or a positive. I'll need to go back and carefully analyze the ordering I'm doing to determine what the check should be. Should it be 0 greater than the result, 0 equals, or 0 less than? Why don't I leave that as an exercise to you to verify, convince yourself that saying 0 greater than the result of the comparison is the right one. Aha! Time for a little quiz. Everybody ready? Okay. Here we have a student record, and it's not that much of a surprise, is it? Looks exactly like the one we've been working with. Now, records aren't variables. Type defs don't give us variables. But the next line does, gives us a variable named A, which is an array of student records. Okay, here are your quiz questions. What you're to do is to take each one of these little expressions and answer a very simple question about it. Namely, what is its type? Now, in most cases, there's only one right answer. In a couple cases, that right answer can be described a couple of different ways with very slight differences. You want to do one together? Okay, how about A? What is the type of A? Now, the person in the back says array. You are halfway there, but that's not enough. Saying that something is array isn't a full description of its type. Okay, any other answers? How about struct? Well, there is a student record A there, but that's not enough of an answer either. The only really correct answer is that A is an array of structs. And if you really want to be detailed about it, you ought to add the dimension information, the size of it. Okay. Okay, let's go on and do another one, a little fancier one. How about A bracket 4.id? Okay, that's the same A. So in case you're tempted to just lazily write down array of structs, that's not going to do it either. We need to pick this apart and get down to what the type of the overall expression is. Well, let's take it a step at a time. A is an array. A sub 4 is not an array. It's a struct of type student record. Okay? Now, when I apply the dot to that, I no longer have a struct. What I have is the type of that thing that I'm pulling out, and that's an int. So the one and only correct answer for this one is int. So now I challenge you to take the rest of these and see if you can work out the answers to all of them. There might be one thrown in here that's completely invalid that the C compiler would complain about. I'm not saying there is, but just be wary. Always good advice when taking quizzes. Data structures occur so often that after a while you get to be pretty familiar with the process of analyzing them. Often we start with the smaller pieces and work our way up to the largest ones. Here is a problem that I'll present for you to think about or perhaps discuss with one another, but I won't present any code for. Let's start at the top. Suppose we want to keep information about one song on the computer. Okay, your favorite style of music. What kind of data would you need to keep or would you want to keep? Okay. And what would you think about to answer that? Well, you'd think about what kind of information is commonly used to identify or to reference or to search an individual song. Then think about how you would organize this information and how it would look in C. What kind of a declaration that might be. And a hint, that might be something that starts with an S. Now let's go on. Once you've got information about a song carefully analyzed, suppose you wanted information about a whole CD of 12 tracks or a 2 CD set with 22 tracks or something. How would you organize that? What kind of structures would you use? Think about it conceptually and then try to write down some C code for it. Not statements necessarily, but just declarations of perhaps type defs, perhaps some sample variables. And we could go one further step with this. What if you wanted to put your whole CD collection on a computer, like a librarian would do with a library collection of CDs? What additional kind of information might you want, and how might you represent that in C? If you can come up with some plausible sounding answers for this, then you're well on your way to being able to use data structures effectively using the tools of C we've studied. Let's summarize what we've done today. Arrays and structs can be combined and nested to any level. The separate rules for arrays and structs still hold. We haven't made them invalid just because we've combined these two forms of structures. Now, I haven't shown any examples this time, but we could certainly use 2D arrays in all of this too. We could have 2D arrays of structs. We could have structs that contain 2D arrays as components, and so forth, again, to any level that we wish. We did see strings used effectively inside some of our examples. The point is that the world contains an infinite number of objects, and so we need some kind of infinite way of combining things in our program so that we can write programs that effectively represent the real world that we live in and that we're solving problems about. Please join me next time as we continue to explore these topics in computer science.